Bayesian Statistics, law of total probability. We've been learning a lot about probability, events, sets, and then we started talking about what we could do with events, complements, unions, intersections. We have the empty set. We have the axioms of probability, which show how to take events and turn them into probabilities. We have rules for the complement, rules for unions, intersections, conditional probability, the idea of independence, and more on intersections. And notice there's a lot of ways to calculate intersections under different conditions. All right, so here we're going to go to our next idea. So this idea of a partition. What if we have a more complicated event space, one that's not just a single set or event? Well, let's suppose the sets A1 through AK, which sets and events can be used interchangeably, form a partition of S. That if they don't overlap, so our individual sets don't overlap, that's what this AI intersect AJ means, equals the empty set means. So what that also says is that if I union all of these sets together, I get the whole sample space. So here, none of the events overlap, and all of the events cover the sample space, meaning that no event would be left out or any outcome would be left out. Now, add a little more complication. What if we added an additional event B here? Okay, so what is the probability of B? Well, the probability of B would be just find out where B intersects each one of these. Notice that they don't overlap. That's our assumption here. So if we did this, then it would just be adding them together. Simply adding them together would work. Okay, so, and we could write this a variety of ways. This is probably the most common way of seeing it because it's written in terms of conditional probability and it shows up later. But either one of these are equivalent to the law of total probability because we're adding up, totaling the probability, okay, across a partition. Okay, so let's look at an example of this. There's a professional amateur hockey shootout. It's set up for an intermission event. So there's going to be this, during a hockey game, there's intermission, and there's going to be this shootout. So it's known at the shootout that 8% of high school amateurs will score a shot. So if they went out there and they slung the puck down the ice, 8% of them would actually score. 11% of college amateurs will score, and 18% of professionals will score on a shot. Furthermore, it's known that 53% of the participants are going to be high schoolers, 29 are college students, and the remaining are professional hockey players, right? It's no fun if the professionals don't go out and sort of screw up and make fun of themselves. So on what we want to know is on any given shot, regardless of who's shooting it, what is the probability that a goal is scored? So we're not going to pay attention, just randomly pick a shot and see whether a goal is scored. Well, the first thing we're going to need to do in all these problems, and this is going to be something that you'll have to keep going with throughout this course, is write down what you know. Okay, so what do we know? Well, from our first bit here, we know that a score given their high school student is 0.08. That's the probability. The probability they score given their college student is 0.11, and the probability they score given their professional is equal to 0.18. We also know the probability that they're from high school is 0.1 or 0.53. The probability they come from college is 0.29, and the probability that they are a professional is 0.18. So I have the pieces that I need. Now all I need to do is put it together. So the probability that I score, or there is a score on this attempt, is the probability of score given high school plus the probability of high school. Probability of score given college times the probability of score of college, the probability of being in college, plus the probability of score being a pro times the probability of pro. And this right here, we're totaling up the probabilities. And you can see why conditional probability sort of makes sense here. So you just plug in the numbers that we had above, 0.08 times 0.53 plus 0.11 times 0.29 plus 0.18 times 0.818, and you do all the math, and you end up with 0.1067. So on any given shot, there's a probability of 0.1067 that a goal will be scored. So a little above 10%, which is probably not what you would have guessed based on the numbers looking at them. All right, so this is our quick example. We're going to keep seeing more examples of these as we go along, but this is our first one. And the key here is write down what you know. And that's probably the hardest part about these problems, because the rest, once you figure it out, it's just arithmetic, and that's pretty easy with a calculator. All right, so notice I've added this rule hiding down here into our list of rules. We've got rules everywhere here now. And now that we're this far, we can jump into what's called Bayes' theorem and actually define it and do an example of it or a couple examples of it, and then move into Bayesian statistics. And that will be what we're going to be shooting for. So we'll move on to the next video, and I'll see you there.